Okay, here are the integrated one notes for 5.1.3 exponential decay. All right, we're actually going to start working with this equation officially in our notes. Imagine that you drop the ball with a rebound ratio. Okay, here we go. The rebound ratio, that's going to be our multiplier. So I am going to go ahead and identify that as B for my equation. From a height of 200. Okay, from a height of 200. So that means that the ball has bounced 0 times. So 0 bounces. And it's got a height of 200 centimeters. Okay, if it has 0 bounces, height of 200, I think this is my 0th term because it hasn't gone anywhere yet. And I let the ball bounce repeatedly. Okay, so I am holding the ball and I'm dropping it. No pressure behind it. I'm going to predict the ball's rebound height. Okay, ball's rebound height after each of 6 consecutive bounces. All right, so we're just going to write our equation here and see if we can figure this out. So my equation is going to be that T of n we talked about last time. It's going to be A times B to the nth. So T of n, my explicit equation, dropped from 200, so no bounces, it's at 200. The multiplier is going to be the rebound ratio, and then n is going to represent the number of bounces. Okay, so let's go ahead and identify some variables here, and then we can use this. So n is going to be the number of bounces. And then T of n is going to be the height after the bounce. All right, so now that we have this, I think we can actually just start plugging stuff in. So if I have no bounces at all, I plug 0 in, so no bounces at all. I'm going to type this into my calculator, and I get 200, which is exactly what I expected. Because if I haven't dropped it yet, it hasn't bounced yet. So I'm just sitting there holding the ball at 200 centimeters. All right, let's see what happens after 1 bounce. So we're going to take our equation, and then we're going to put 1 in for the bounce. Because what we really want to do, if we were to set up a table, which I think we're going to do here in just 1 second, we would take the original drop height, so this is my number of bounces, and this is the height. In the beginning, it should be 200. The rebound ratio, that multiplier, we would times by 0.714. which would give us that 142.8. But then we would just keep letting it bounce. So I would multiply by 0.714 again, which means, take a look over here, this extra multiplication. So at this point, I would have times by 0.714 at this level, but then I times by 0.714 previously to get to that answer. But remember, exponents represent repeated multiplication. So I can take my 142.8 and times it by 0.714 and get 101.9592. I can get the exact same thing by plugging 2 into my equation. And I would like you to test it out. So actually plug this into your calculator, and you will see we get 101.9592. And then we continue. So after 3 bounces, we would have multiplied by the ratio 3 times. So if we type that in, we would get 72. Notice the ball isn't bouncing as high as it was, which is exactly what we expect. So T of 4. So on and so forth. And go ahead and fill in the rest of this table. So at this point, I have all of the different heights that the ball was at after completing that bounce and coming back up to its maximum peak before it starts falling back down again. State the common ratio or the multiplier. Well, it's that thing we kept multiplying by repeatedly, which in this case was the rebound ratio, was 0.714, and that is B in our equation. State the 0th term. Okay, 0th term was when the ball was not yet dropped. So its original drop height in this case, which was 200. All right, write the explicit equation. Well, we've already done it. It's up there up at the top. So it's T of n is equal to the original drop height, the multiplier, and then we do want it to be in terms of n and T of n, so it is generic. We can use it for anything. Okay, moving on. What are the independent and dependent variables in the situation? All right, well, I'm going to think about independent means what we are plugging in. So in generic terms, independent and dependent will become more solidified in future classes. So I'm going to think about what am I plugging in? And I'm thinking about the equation. Well, the thing I keep plugging in is n. So I would say that the independent, in this case, actually in most cases, is the input. So independent input. So that's the n, but n represents the number of bounces. So the bounce. So number of bounces. The dependent variable is typically the output. Well, after the ball drops, we measure the height of it. So this is the height after the bounce. What this should allow us to do is figure out on our graph what represents the x-axis and what represents the y-axis. Well, the x is going to be the independent variable. So we're actually going to put n down here. This is going to be the number of bounces, or which bounce number it is. And then the T of n is typically going to be your dependent variable, and that's our y. So we're going to say T of n here. And this represents the height. So what we want to do at this point is go through and plot the points that we've got. Okay, so it doesn't have to be exact. We just want to make sure that it's kind of ballpark here. So I am going to change the increments on each of my x's here. So I'm going to go 3 boxes to represent 1. Hopefully that'll fit. 3, 4, 5, 6. Okay. Then we can actually make them further apart if you would like, or we can actually plug some more numbers in. And then we wanted to start out with a 200 height. So what I would do is actually count the number of vertical boxes that we have here, just to see how much space I have. So knowing how many boxes that I have to deal with, I think I'd probably go up to 30 and let that represent my highest point here. And I dropped this, so back at my equation, looks like I dropped it from 200. So I am going to go up to the 30th box and just let that represent 200. After I have that identified at 200, then I would say about halfway down is going to be 100. So you'll see that I went in increments of 10. So I'm going to go dead center between these two. So right there would be 100. And then dead center between those two. And again, it doesn't have to be perfect. Okay, so right there would have been 50. So I'm just going to keep cutting the number of boxes that I have in half approximately. Okay, now we're just going to do the best that we can with what we got. So we're going to graph the predicted rebound heights. Okay, so at 0, ball didn't bounce at all. We are up at 200. So let's go ahead and plot that point. I'm going to plot them in green. Okay, after the first bounce, using what we got, we were able to get a height of 142.8. So 142.8 is a little bit less than halfway between 100 and 200. So I'm going to go ahead and plot a point where I'm at 1 on my graph. So I go down to the bottom. From here, I'm going to go up till about halfway between 100 and 200, maybe a little bit less. So I would say, I don't know, somewhere right around there. I'm going to go ahead and plot that point. And then I'm going to take that, and we would find the next answer, which, just using my table here, is now at just over 100. Just over 100, just barely over 100. So let's say at 2, we're just barely over 100. And I'm only drawing these bright green vertical lines just to help myself find the points. That's all. I'm going to come back and erase them in just a minute. And then with 3, I'm just using the answers that I already did. I got a little over 70. So that's almost halfway between 50 and 100, but less. So I'll go to about halfway, and let's go a little bit less than that. So maybe right around there. And then just filling in the next couple of them. Looks like we got 52 or close to 52. So just like a hair higher than 50. Just a tiny, tiny bit. I'm going to plot that point. So all I'm doing is plotting my points here. Hopefully you kind of see that little curve that's happening. Okay, and then the next one was 37. So a little bit more than halfway. Say it's about there. And then at 6, we were at about 25, so pretty close to halfway up to 50. So probably around there. Okay, those are the points that I have connected. So let me go ahead and get rid of my green lines that I put on there, since they're not technically part of the graph. They were there just to help me figure out where the points were, because we've got so many boxes here. Okay, so those are the points that we found. Go ahead and plot them. Graph the predicted rebound height. Okay, done. Should the graph be discrete or continuous? All right, so are we going to connect the dots or not? That's the question. Well, let's think about this. Let's take a look at what the x-axis represents, or the n. Down here, this represents the number of bounces. So I guess my question to you is, would it make any sense to have a 1.5 bounce? I want you to think about being in line again. If you're in line first, the person behind you Are they at the 1.5 spot or are they at the 2 spot in line? I think we can all answer this and say, we don't want to connect the dots. This thing needs to be discrete. And the reason we say that is because n, just like before, cannot be a decimal or a fraction or negative So same rules still apply as what we did previously with arithmetic sequences.